We already have enough attendees, and the session started to be recorded. Great. So today we start our second online event. We normally have it physically once a year, but due to COVID times, we have to adapt to ourselves. And we also wanted to have a short session, not a long one. As I can see today, there's sort of long fatigue of attending online meetings, so we try to make it a more informative and more entertaining presentations, so people can learn about us and what's happening in the industry with regards to VR. So again, for those who just recently joined, please, if you want to participate, put questions or anything, just take a picture of this code and use your phone to participate later. So the agenda is as follows. We have a short introduction about VRIF, and basically I want to present what actually are doing with the topics of 5G volumetric video in our VRIF guidelines. And then we have 3 sessions separated by one more on research, another one on standard, and then another one what's happening in the industry. So we welcome our speakers from Fraunhofer HHI, from Tencent, advisor of 3PP, and Air France technical advisor Jay Maloney. So a little reminder, there is a statement. It's to further widespread availability of high quality audiovisual VR experiences for the benefit of consumer. We started in 2017, and at the beginning was VR 360, but today we extended the scope to address also XR experiences, which is also AR, reality, and virtual reality. So this is our membership today, as you can see here. You can have also look at and they participate mostly on the sessions on VRIF when it comes to contribution for the guidelines that we meet regularly every week. And a little bit updates. Not going to go in detail on these ones, but you can later have a look at very good material on what actually we do in VRIF. For instance, we have a newsletter. You can join there and get a quarterly newsletter. We also have released new guidelines every year. We are in the version 2.3, and it's mainly related to the VR 360 track. And I'm happy to say that we were the first to propose a profile for VR, and then later we updated unconstrained HVC-based viewport independent and dependent view profiles. And also we talk about recommendation and best practices around multi-viewpoints and overlays. For instance, you can use this for targeted advertisement. So basically you can monetize your VR content. And also we have a collaboration with the Streaming Video Alliance, where we test 4K and 8K VR, and where we have a quality of experience with the Streaming Video Alliance open caching solution. So far I've been tested with fiber infrastructure, but later we will do 5G test on real networks. And the last year we were busy being different events, and mainly they were online as the world has to adapt to that. And all the presentations and links and videos you can download directly without being a member. Just go to the webpage. You have all the links here. And you will get all these links when we publish the presentation. So a little bit what actually we do. The current work of VRIF is divided in 4 parallel tracks. When we started, we only work on VR 360, which is basically streaming the VR in a 360 degree. And we deal with a lot of guidelines how to capture the content, processing the content, and deliver and distribute via streaming. But then the scope of VRIF was expanded to adapt with a new immersive experience. And then we have a track which is volumetric, which is the main topic of the session today. Social VR, which is related to how people talk each other in the context of VR experiences when when they have remote meetings, for instance, and how that breaks the barriers of isolation. And also we have a track on 5G cloud, which is a way to see how we can improve the quality of service of VR XR experiences using 5G cloud infrastructure. So today, basically, we're going to talk about volumetric and 5G cloud. So what about use cases? We have the volumetric streaming of assets, which basically you capture a person, for instance, with camera array, and then you deliver that asset to your screen, for instance, a broadcast. This picture is taken from BT Sport, for instance, or you can have a live sport personal view. So you have a big setup where you have cameras around the stadium, and you can capture different angles and create a free point of view. So basically, the user can choose that you are in the middle of the stadium and feel what's first-person view of a real event. And for instance, you can also use a social VR improve experience. Instead of having an avatar, you can create your volumetric representation of yourself and use that one to talk to each other, as you can see in the picture here. So you have a sort of use cases that are quite appealing when it comes to communication and entertainment. So the main talk about VRIF today, with the work we do in the guidelines working group, it's about volumetric streaming end-to-end. I'm just going to give a very short introduction, since I hope for people that are going to talk about this quite extensively. But basically, you have a part of capture, how to capture volumetric system, what type of production system you have available in the market, how you process this content to reduce all the information you get to a more easy way to deliver that amount of information. And basically, you have two types of way of distributing the content. One is using point cloud compression, and the other one is using mesh processing. And basically, when you send these assets of volumetric representation of a person, for instance, in the picture, you are able to render in the device. And also, we talk about content security, how we can secure the content end to end. This is something that is not clear yet how we deal with, but this is something that many people who create the assets want to protect their investment and be able to monetize without basically losing the content someone who doesn't want to pay. So the current scope of VRIF, it's targeted to be delivered in the guideline 3.0, and that's depend of many aspects when we will deliver, but we hope to have it at the end of the year. And it's a mix between volumetric track and 5G cloud tracks. Basically, the thing is that volumetric model and assets is a great element for content created to make a feeling immersive experience. And then you have the production, transfer, and processing of volumetric assets requires new and resource-demanding development techniques which can improve 5G cloud edge processing. And the idea is that 5G can facilitate the real-time delivery, which is something that everyone talk about, but we wanted to understand how can we do this. And today, what you see there with production companies make volumetric assets quite good, for instance, for movies, but for delivery to the end user, home user, it's that you actually can see around the object, it's not such a high quality due to the limitation factors such as bandwidth, latency, and also device processing power. This is something that 5G can help you to deal with, for instance, by rendering the volumetric asset in the cloud and let the device, let's say the glasses or the tablet or the TV, do only the video decoding, something that's going to be talking today in the session. So the guideline scope right now is about volumetric and 5G audio video production techniques, how to compress this volumetric format for any display, and how to best utilize key aspects of 5G cloud edge infrastructure, which actually means defining an architecture, how to deploy different processing parts of the volumetric end-to-end value chain. Okay, so that was the introduction on the scope of VRIF. I think I'm very excited to hear about our guest presentation, but first let Tom from TNO to have this question. So please participate in that. Shall I give you the access to you, Tom? Can you?
Yes, that's good. I show you
there
results immediately. They come. And I start also a little timer.
Mm-hmm.
So let's give everyone 1 minute time on give a feedback on a bit on of course, as Mauricio was telling, a big part of our work and what we do is to provide guidelines. And of course, it's good to know from this audience how important these guidelines are, and especially on the guidelines on volumetric video, because that will be most of our work that we'll be doing this year. So please provide some feedback. And we already see some feedback coming in, and glad to see that most of it is coming in the important section. And okay, time is almost up. So we only have a few questions in, and maybe that's also because it was the first question, and some people are still looking for the Menti codes. But let's now continue, and we will come back with a Menti question after each presentation. Thank you.
Mm-hmm. Okay, so now I should share my screen again. Great. So now we start with the session on interactive volumetric video production and streaming. Dr. Oliver Schreiber and Dr. Cornelius Held from Fraunhofer SHI. So which one should I give the role to share? You start first, Oliver.
Yeah, welcome everybody. So are you sharing the slides? And
I'm gonna give you access, or you wanted to do it myself? I can share it, no problem. Let's do that.
Yeah, perhaps that's more safer. Yes.
There it is. Okay. Voila. Okay.
Okay. Yeah, great. Thank you for this opportunity to present some concepts and results about production and streaming of volumetric interactive volumetric video. So I will start, and my colleague Cornelius will then continue with the part on interaction and streaming. So next slide, please. Yeah, so we'll first answer the question, what is volumetric video? But hope most of you know, but let's give some more detailed explanation. Then I will present the workflow, the production and the workflow, and discuss different aspects. And then we will look into interactive volumetric video, the first concepts to make volumetric video really interactive, and then some concepts and ideas about volumetric video streaming, basically to cope with the huge bandwidth data rate which is required by volumetric video. And then we summarize our talk, while the second part of the talk is given by Cornelius. Next slide, please. So the current state for creating characters in virtual reality, 3D characters in virtual reality and augmented reality is usually also in movie production is to create a model and realistic possibly realistic avatar, and then capture the motion of an actor, for example, or some real person, and then combine this model and animate the model with the captured motion. So that's the way how all these animations are done in the film industry and so on and so forth. So, but there are several issues. First, the realism is lacking. Facial expressions cannot be fully captured. Reconstruction of dynamic behavior of clothes is quite challenging. And there is a limited complexity of motion which can be tracked and then transferred to the model to be animated. So therefore, click please. The volumetric video approach is to capture a person directly with plenty of cameras and create the 3D model out of it. So we have real 3D, dynamic 3D representation of a human being, of a person. And so we can capture everything, facial expressions, motion of clothes, and so on. And the result is a sequence of meshes at first stage, or a sequence of point clouds. And this is then a data format which can be used for render engines to be watched from any direction, from any perspective in 3D space. Next slide, please. So there are several capture studios available nowadays in the world. So we developed one of the first prototype systems in Europe at Fraunhofer HHI. After that, we founded 1 year later our spin-off company VoluCap in Berlin, Potsdam, Babelsberg. And obviously, Microsoft is doing a great job and worked also quite several years on this topic, and they built up several studios already on the West Coast in US, but also in London, for example. Volograms is another startup company founded in Ireland, in Dublin, and another important studio is also 4D Views, in a company in France, which worked on volumetric video since several years. Next slide, please. So in general, this figure has already been shortly presented by Mauricio. So if we consider the whole workflow for volumetric video production, first we need to think about how we get our data, our 3D data from a given scene. So there are basically two different kind of inputs. One is pure RGBD acquisition, where you get immediately 3D data from sensors. And the second approach is the top one, where you have several sensors, but apply computer vision algorithms to estimate the depth. Then you will have the depth from different perspectives, and this 3D information needs to be fused, and then you end up with the 3D point cloud. So this is then again a point where you have to decide how to proceed, and there are basically two approaches. The first one is the point cloud based approach, where you do point cloud coding, and with the coded point cloud you can then stream and decode on the receiving side, or you follow the mesh-based approach, where you create meshes from the point cloud, do mesh encoding, and then stream them encoded mesh to the receiving side. Next slide, please. So let's dive in a little bit in the workflow itself. So here we'll not go in detail on all the different blocks, but what is important to mention is if we look at the amount of data which we have at the beginning during capture and what we get at the end of the workflow, you can imagine that this is really a big challenge, and the art of science is to reduce the data in all parts where the information is not necessary, and keep the necessary information in terms of geometrical detail, but also in terms of texture. So I gave here some figures, and on the capture side, for example, we have around about 1.5 terabyte of raw data, 1 minute of volumetric video in our capture stage. If we do all the 3D data processing and end up with a point cloud, we still have 34 gigabyte of data for 1 minute of volumetric video. When we then further process the point cloud, create a mesh and do the mesh reduction, then we end up with a third of this, ending with 13 gigabyte. And finally, if we apply our mesh encoding on this volumetric data, then we finally end up with 0.7 gigabyte. So this is a tremendous amount of data reduction with the overall aim to keep the level of detail in terms of geometry and texture. So next slide, please. Yeah, here are some examples of the different processing steps presented. On the left-hand side, starting with the depth map, the point cloud, the mesh point cloud, the reduced mesh, and finally on the right-hand side, the reduced mesh with texture. Next slide, please. Yeah, and that's the point where I hand over to my colleague Cornelius. I'm happy to have you here. Welcome and continue.
Yeah, thank you, Oliver. Hello, everybody. And thanks for giving also to me the opportunity to present some results here. Yeah, first, what you see here on this slide is so what Oliver presented is you capture volumetric video, and computer graphics, we know that we can also animate 3D graphic. And we developed an approach where we can apply this animation also to a captured volumetric video. You see that here in this video on the left side is the captured volumetric video. And by applying our method, which uses an underlying shadow mesh model, which is glued to the volumetric video scan, so we animate the shadow mesh and apply the animation onto the volumetric scan, we can animate the head here in this example. So by that, we can introduce interactivity also in a volumetric video. You will see this later in a demo. We integrated this into our prototype implementation that you will see on the next slide. You can find more details here in this publication. And maybe we go to the next slide. So that's the animation part. And here we go. Sorry, Maurice, you need to click a bit here. There's some animation. Sorry for that. So now we want to stream this volumetric video. As you saw from the figures given by Oliver, there's for high quality volumetric video, as we are dealing with here, it's a significant amount of data. And also, if you want to play this on a mobile device, there's also a lot of rendering complexity involved. So we came to the point where so the problem is the complex rendering, and the solution is that we developed or we're working on is to offload the rendering to an edge cloud server and only transmit a 2D video based on the user's head pose to the end device. This is also called split rendering, and it's discussed in standardization also. That's quite well-known approach. The drawback here is, of course, you need a very low latency system and network. So the overall system needs to be optimized for latency so that the user doesn't recognize that this is rendered in the cloud. I will give more details on the next slide. Please, Mauricio, if you can proceed. So that's the system that we implemented, just a higher level overview. We have an edge cloud server. We have a volumetric file. So this is coming from the production process Oliver explained. We can use here any format that is usable on the edge cloud server. Then we play that video. We implemented this in GStreamer, and the decoded video and the mesh is going into Unity, where we also apply this mesh animation. So we manipulate the mesh in Unity based on user input. And this is the rendered 2D image. So we adapt the camera in Unity to the viewpoint of the user. So there's always a signaling coming from the client to the server, and we render that camera and send the 2D image to the video encoder, user NVIDIA graphic card here, so nothing specific. Then we have a WebRTC channel here, where we send the 2D video stream to the client. We decode it and project it in a AR mixed reality framework. We render it there, and then it's displayed on the client side. And as mentioned from the client side, there's always a position update, send it back to the server. So that's a high level overview. If you go to the next slide, then you will see more details of the system that we developed. Maybe please one more. Exactly. That's a more detailed system. So you see the volumetric video player, the GStreamer, then you see the media pipeline. So we can use whatever video decoders exist here. For example, for the mesh encoding, we used Google Draco. For the video decoding in the current system, we use H.264. But of course, this also can be applied for used with H.265, H.266. And then the decoded video is going into the Unity 3D, and then it's sent to the cloud rendering library, what we call. So that's a WebRTC protocol stack, also implemented in GStreamer. So everything is done with open source tools here. We also have a prediction engine that you see in the cloud rendering library. So we try to predict the user position, so where it will be in the next 60 milliseconds. And this gets important if we want to bring the latency down. So I will show that on one of the next slides. So if we know where the user will look at in the next 60 milliseconds, we can save some latency on the network. Yeah, please, next slide. I think you need to click a bit here. This is going, there's some animation in here. So that's maybe interesting here, some measurements on motion-to-photon latency. We set up our system on an Amazon cloud instance. If you can go back, thanks. We set up our system on an Amazon cloud instance in Frankfurt. We have a browser WebXR implementation that is receiving this WebRTC stream and is generating a volumetric, mixed reality scene environment. It's connected over wireless Wi-Fi to the internet. And what you see here is that we end up with the overall system. So this includes sending back the feed, or having some event on the client, sending back the position update, rendering, encoding, sending back. So it includes the whole latency chains of motion-to-photon latency. And in average, we end up with 58 milliseconds at the moment. And as you see here, the details, 16 milliseconds is coming from the network. So if you put that on a 5G network, this will be reduced. If you put it in edge cloud in 5G, then on the media pipeline, so that's with 70 frames per second. Sorry, there's animation here. It keeps you busy, Mauricio. So we have 70 frames per second. So we run, this is with X264 encoding in the cloud. So we run the X264 at maximum speed, 70 frames per second. This gives us 60 milliseconds for the encoding. And the rest, 26 milliseconds, is coming from the browser. So there is no optimization on that side. So we have also an Android implementation, and we also have an implementation for Nreal glasses, also based on an Android phone. And this 26 milliseconds can be reduced also by optimizing the client-side implementation. As you can see here also in that conclusion, client processing going to higher frame rates is also a solution to reduce latency 5G network, and also adding this user prediction. So if we have this 60 milliseconds for motion-to-photon latency, but we can predict 60 milliseconds into the future, and we know where the user will be, then we can really absolutely minimize that latency. So that's something we're currently working on to get these latency numbers really down to an absolute minimum. Maybe the next slide. So demo time. I have a video here that tries to show what we have. So that's an Android implementation. Here you see in the back the server, the Unity server, and you see that the user can. So we have 3 objects here rendered in parallel. So that wouldn't be possible without if you would play them locally. So these are 3 high resolution objects. And here you can also see how the user would see that from Nreal glasses. This basketball player is interactive, so you see the head rotation. It follows the user. Yeah, and you can walk around, and it also gives you a stereo image, because we render in Unity, we render stereo frame and also transmit the stereo frame. Yeah, so that's maybe if you'd like to can play it again.
Yeah, did you hear the audio or not?
As I heard the audio at the beginning at least.
Okay, then I do it again.
So we also, concerning the audio, we also render spatial audio. So we do it the same approach. We render it on the edge cloud and transmit the rendered audio to the user. You can also see the latency here. This is really minimal.
Don't need a basketball arena to be great. You can practice whenever, wherever. I'll see you at the next telecom basketball game or in the headset. Hey,
yeah,
our training session. Don't need a basketball arena to be great. You can practice whenever.
So the nice thing is that we can really integrate multiple of these really high quality volumetric assets into a scene, and have also this dynamic approach with animating these objects. So yeah, if you go to the next slide, I think then we are getting to the end of the presentation. Oh, you want to show it again, Mauricio?
It's not showing. Maybe.
It's a pity at the moment that we cannot really show the Nreal glasses due to this Corona situation, because this is really impressive to see. So if we go to the next slide. Yeah, this is already getting to the end. So you can find more information. So we have a web page where we collect some information, some recent publications. There's also next week, April 27, there's a high table briefing on volumetric video streaming. We will show a live demo there. If you're interested in, go to the webpage, register, and there will also be more details on that. So then next slide, I think then we are at the end. Yeah, thank you very much for the time, and we're ready for questions.
Connor, yes, we have time for questions. If anyone would like to ask a question. Well, I guess I have one. What was the bitrate for the demo you used with speed rendering?
The bitrate you're asking?
Yes.
Well, that's around. So since this is plain 2D video, it was something around 6-8 megabit per second, something like this. So it really depends. So we don't send the whole viewport. We only really send the object itself, the rendered view of the object, and then it depends on the size of the object in the viewport. So if it's really there's a small size, then the bitrate can really go down to a very low number. If it's in the full screen, then the bitrate is higher because of the size gets bigger. So you can think about typical bitrate numbers coming from 2D video. This on the last mile.
So following that question, when you actually, before you have mesh encoded data, what was the bitrate before you decoded in the cloud?
Yeah, so we said we use Google Draco for the mesh encoding. We use H.264 for the texture, and with the current format that we get from the production side, this is roughly 40 milliseconds, including 40 megabit per second in total. Roughly, it depends on the content. It depends on a lot of things, but this is some figure which, yeah, 40 megabit per second.
Okay, so it's from 40 to 6 megabit per second with rendering. That's okay, interesting. Mm-hmm.
Yeah, I mean, if we sent 3 objects, right? 3 of these objects. So each of it has 40 megabits in the source file, and then we render a video, and this gets down then to these megabit numbers. So yeah, if you have multiple objects, then the bitrate reduction is more significant.
Mm-hmm. Okay, thank you. So we have Tom who hijacked my screen. So maybe you can apply another question here. Which one you think volumetric video streaming will be more benefits for this one? Which industry? If it's entertainment. Okay, we have people answering. Good.
Of course, in the meantime, if anyone else still has a question, Hofer. Of course, you can always put also your questions in the chat. We can take them up during the session or afterwards.
So it looks like sport entertainment is getting the winner now. Okay, so the winner is entertainment, and then second spaces education. Very good. So now we shall start screening my screen again. We have our next speaker, which is Gilles Tenu from Tencent and Vice Chair of the Video Working Group in 3PP. We're going to talk about standardization of XR over 5G. So hi Gilles, I'm going to give you access to, so you want to share yourself. You have a Tencent, there it is. A lot of people that can, you got it, okay, great.
Okay, can you hear me well?
We hear you well, welcome.
Okay, excellent, thank you. Okay, hello everyone, thanks for giving me the opportunity to share the latest developments and ongoing works in 3GPP SA4 in the field of extended reality. So after a very brief introduction to 3GPP, I'd focus on our initial study on XR over 5G that served as a basis for triggering other activities such as the XR traffic characteristic studies, the glass-based AR services, the streaming architecture for edge processing, but also a few words on 8K VR360 operating modes and immersive communications. First, for those of you who are not familiar with 3GPP, a bit of context in which we are working. This now pretty famous triangle describes the vision defined by the ITU, IMT on the future of digital networks, and around those three edges, enhanced mobile broadband, massive machine type communications, ultra reliable and low latency communications. 5G has been developed by 3GPP, and the media aspects are concentrated between the increase of bit rates and the reduced latency. So it's more located on the right face of the triangle. And 3GPP works in releases, which means that specifications are constantly evolving so as to integrate new functionalities depending on the market demand and the member support. 5G was first delivered as part of the release 15 in mid-2018. And the following releases provide additional features on top of the main 5G core and 5G system architectures. We are now under release 17 that is running until March next year. And the release 18 will also be based on 5G. So for 6G fans, please be patient. SA4 is the codec and media working group in 3GPP and is tasked to develop specifications that ensure the interworking of media services, streaming, and conversational. Among its activities, many of them are now focused on immersive media in general. And with regards to extended reality, we had a significant study that was completed in March last year. And consequently we launched various activities so as to refine the identification of gaps in existing service architecture and device functionalities and capabilities. So I'll come back a bit more in detail in most of those activities, but in very brief, the glass-based AR/MR study focuses on architecture and device impacts on AR services over 5G. The streaming architecture for edge computing is tasked to analyze the evolution of 5G media streaming architecture in order to integrate edge processing functions and requirements. The traffic characteristics study has the goal to provide operational information and quality indication of XR media delivery depending on the 5G radio configurations. A normative work is dedicated to provide the support of 360 video streaming in 8K resolution, and there is the ongoing effort for the definition of IVAS, that is the 3D extension of the 3GPP homemade codec EVS. And immersive communications are also enabled thanks to the efforts in enabling 360 VR conversational services. And as part of the release 18, I could also mention the work on terminal audio quality performance and test methods for immersive audio services that is called ATIAS. So let's see how 3GPP initially addressed extended reality with the study called FS 5G XR. And this study was triggered to primarily put a definition behind XR and identify what it means in terms of quality of experience. So we collected a large collection of use cases addressing different types of consumption, streaming, conversational, interactive, as well as representation formats and candidate technologies. And all the findings are collected in a comprehensive technical report, so the TR 26.928. So I invite everyone to have a look at it. It's a pretty significant piece of work. And as I said, we provided a list of definitions in terms of degree of liberty, reference coordinate systems, definitions of concepts of presence, formats also such as meshes and point clouds, techniques like asynchronous time warping that is implemented in ultra-low latency environments. And here is a list of use cases identified with their associated type of reality, AR, MR, VR for augmented, mixed, and virtual reality, the degrees of freedom, the type of delivery, and the target device. And in the technical report, you will find for each use case an analysis on the feasibility and examples of existing services and potential standardization needs. So as part of the study, it was also important to categorize devices depending on their functionalities. And some devices rely on external entities for some processing. Others are fully standalone in terms of media processing, but also in terms of radio connectivity. Some aspects addressed were latencies and delay, with some requirements identified depending on the scenario. On the latency, although we identified that less than 20 milliseconds motion-to-photon latency, so from the time you move your head to when you see the display change was required, we have also listed requirements for ultra-low, low, moderate, and non-critical latencies. We also selected technical requirements for visual presence, for instance, for spatial resolution in VR, 2K by 2K per eye provides acceptable quality, 4K is considered as the next step, and 8K being the ultimate goal for temporal resolution. Sustained frame rate of 90 frames per second and beyond are likely required despite the usage of asynchronous time warping, for instance. So here is an example of a split rendering architecture in which the pose of the user is sent to a server that may be located at the so-called edge, and that computes the scene to be rendered and send it back to the user equipment for rendering in a timely manner. And finally, we decided to consequently launch more activities such as the focus on glass-based AR and MR services, the development of a framework for split rendering, the documentation of XR traffic characteristics, and the extension also of the multimedia telephony for enabling immersive services. So with regards to the study on XR traffic characteristics, it was launched almost a year ago with the objective to collect traffic characteristics for immersive media services, including downlink, uplink data rates, taking into account delays and packet error rates, and deduce the impact on the quality of experience when such media cross the 5G network, which is kind of a challenge due to the complexity of simulations and the many parameters to be incorporated. Some options were to rely on realistic system setup with measurements, to measure existing services, to break down the system into smaller pieces, but some approaches were identified impracticable due to the complexity. And the basic challenges were to evaluate basic system design options and their performance, to generate traffic models for the evaluation of the radio access network options, to provide guidelines for good parameter settings on encoding, content delivery, and also how to define the appropriate parameters for the radio access, and to identify also the capacity for such type of applications, to identify potential optimization on the codec side, the protocol, the system aspects. So there's a lot of opportunities around this traffic modeling, and it's just the beginning of this effort. So what we decided finally was to define the traffic model using source contents that are converted into video traces, the so-called V traces in the figure. And on top of the figure, the encoding configurations associated to different scenarios allow for the generation of the simulated traces. So that's what we call the S traces that are also converted into P traces, incorporating content delivery models. And those traces are then sent to the radio access network experts who will apply different network QoS parameters. So these are the configurations operated by mobile network operators, such as latencies, packet error rates, maximum bit rate. And 3GPP SA4 will then run the inverse process and will have to define a model for evaluating the impacts on the perceived quality. So for example, if we realize that a packet associated to an intra-frame has been lost or has arrived too late, the consequences on the perceived quality won't be the same as for a non-reference picture or just a slice of it. A few words now on the study on 5G Star, the glass-based AR and MR services. This recent study aims at addressing the following points. So identify the functional features of AR glasses, focus on a limited set of use cases from the initial study on XR over 5G, define the architectures and media flows, identify the media formats that are exchanged between different equipment, and also identify the content delivery protocols and the capability exposure. During our study, we identified the need for differentiating device types depending on their functionalities and also their connectivity. And the two main types are the first one, the first one that is called STAR, standing for standalone AR UE, and the second one, EDGAR, meaning edge-dependent AR UE. So a UE is a generic term used in 3GPP for describing a user equipment. And here is a list of the use cases identified so far. These are extracted from the previous study, for which a mapping to a media service architecture is required. As an illustration, this figure describes the mapping of the standalone AR device to the 5G media streaming architecture. All the APIs, M1D, M up to M8D are already defined as part of the 5G media streaming architecture. And the ones circled in red are expected to be updated so as to support the AR scenario. And same here, same illustration for the 5G edge approach that breaks down some functionalities initially supported by the user equipment in standalone mode, and that are shared with the edge in this configuration. So this ongoing work still needs to refine the procedures and all the code flows between the different entities for identifying also the protocols and APIs to be updated. The content formats and codecs also need to be analyzed, as well as key performance indicators and QE parameters that are likely to be converted into media service requirements. We will also need to use the findings of another SA4, 3GPP SA4 study on edge processing architecture for streaming services. Now, a few words with regards to the 360 VR operating point for streaming services. So 3GPP SA4 has already defined a list of operating points for VR 360 streaming services. Those are listed in the 26.118 specification, and they are recommended in the 5G media streaming service specification under the VR profile. So this is a 26.511 specification. And given the capacity of both the radio access and the latest devices, we have decided to add the support of 8K format in viewport independent streaming mode. And thank you, VRIF, for the support and the productive exchange via liaisons. We will also incorporate traffic characteristics information on the 8K delivery. And we will need to, we still need to finalize the support of HLG that will not only be associated to 8K, and we will provide operation point recommendations into 5G media streaming services. Finally, ITT4RT is a normative effort focused on enabling immersive experiences on top of 3GPP conversational services. The objectives are to refine the audio and video codec configurations, the media constraints, and RTP formats, including SDP configurations and the appropriate signaling mechanisms, for instance, for enabling viewport-dependent delivery. The first phase has just been completed and now offers a basic real-time 360 VR experience. Some updates to the SDP configurations are provided, as well as capability exchange and some overlay configurations. Audio is for the moment limited to what is already specified in the multimedia telephony specification, which means that it's not specialized. But there's a second phase that is going to focus on the improvements of the QE with viewport sharing, the definition of a dedicated QE metrics, some evolutions are expected on overlays, some investigation around the use of RTP-based signaling for the supplemental enhancement information messages, or the SCI messages, and hopefully the support for immersive speech audio codec, either based on multi-track or multi-tracks of EVS or IFS. And yeah, that's pretty it for most of what is going on in 3GPP SFR. Thank you for your attention.
Thank you, Gilles. So we actually have one question in the chat. So have you also evaluated the problem of the divergence accommodation in the devices? That's from Stefano Bonora.
This is, well, this is a problem that has been identified. We haven't seen any, it seems more to be device specific, and this is basically out of our scope in 3GPP. So in 3GPP, we are not defining services, we are just defining technical enablers that will enable those services to be deployed by any service provider, maybe jointly with mobile network operators, or mobile network operators, maybe jointly with third-party service providers. With regards to this divergence problem, this is something that has been identified, but there's no technical requirement that could be put on the devices that have been identified so far. It could be part of a certification, device certification process, but this is out of 3GPP competence.
Thank you. Is there any other question for Gilles? Okay, so we have the Mentimeter in the meantime.
Yes, and this question is same one as we asked in the first open session of VRIF last year. And so we want to see indeed how this audience thinks about it. And yeah, we're almost six months later. So how things evolve around VR in 5G.
Okay.
So now it's time for Jay from Air France KLM.
Okay. Okay. Good afternoon. Can you all see me?
Yes, we see you.
Okay, cool. I'm going to attempt to share my screen. This is a completely new meeting program for me. So, okay. Your entire screen, share screen, and application window. I think I have to do this one.
It should be in the bottom.
Yeah, I'm trying to get. Yeah, okay, it's starting to share now. Where's my presentation? Here's my presentation. Do you all see this?
Yes, we see.
Okay, cool. Okay, let's start at the beginning. Okay, short introduction. My name is Jay Maloney. I'm an IT consultant within Air France KLM. My specialty is new technology. So everything to do with XR, quite a lot with AI, IoT, blockchain, that sort of technologies. And Tom asked me to come along today to talk to you about what we're facing, issues we're facing, and solutions that we maybe having regarding XR at the moment, because as a company we are really interested in this technology. So I'm going to give you we don't have much time, I know, so I'm just going to give you a quick glimpse of what we're doing. At least I'll give you an idea. It's not going to be a deep technical thing, because this is more about our customer and how we're starting to utilize these technologies now. So I'll just we'll start. Okay, so going back, these are technologies which we are looking at within Air France KLM at the moment. As you can see, the one on the right side, the pilotless transport system. Every time I talk to our pilots about this, they're not happy. But it's something which is possible. You know, it's technically possible already. So, you know, we're looking into this. Augmented reality and virtual reality are very, very, very big drivers to us at the moment. They're technologies which we're really utilizing. Of course, big data, everything about our customers and Internet of Things. And we use a lot of AI within our hangars, where the aircraft, they come in and they're scanned, and millions of photos are taken, and we've got lots of algorithms going behind it to automate our maintenance tasks, which is really starting to good. So in a nutshell, you know, this is where we're looking at the moment. These are things that we're doing. A few of the experiments which are going on at the moment, which we believe in as a company. Virtual traveling. We're convinced that virtual traveling is going to be a big market in the future. It's something which we want to utilize and get a hold of now, and we're really looking to experiment with this. And this is not 360 static. You know, we're talking about live traveling. I was just looking at that question just now. Do you think 5G will help VR? Of course it will, and this is where it's going to really be a big advantage for us. Telepresence. Air France KLM, they fly back and forth to France the whole time, back and forth. We've got lots of mixed teams. 30 million a year we give out to you know, it costs us to fly back and forth. Environmental aspects, everything like this. So telepresence, virtual reality is a big thing. We're using it now. We use it today to meet. We have lots of Scrum teams in India, in Poland, in France, wherever, and we use telepresence, virtual reality to meet. We use a platform called Glue, which is from a Finnish company, and it's really cool. Onboarding, we have lots of people out of India who come to the KLM to work. That onboarding process is really a challenge. So we've decided to automate this using virtual reality, and this is really starting to deliver. We want virtual reality also in the aircraft. We want to offer people an opportunity to experience virtual reality in the aircraft. Your own entertainment system. You know, you can bring it from home. You've got your own films on. You can actually sit in your living room and watch your entertainment. And of course, our BIM design for Schiphol and KLM. We want to automate this. We want to be able to go into environments and look at 3D blocks and that sort of thing. We're also digitalizing on the other side lots of virtual reality trainings, cabin crew. Predictive maintenance, we're using AI and AR together for predictive maintenance within our operations environment. We like the fact that you can see things in 3D, and you can go around things and take things out. It's really cool. Same thing, machine as a service, Alexa, incident management. Our big data, quantitative data and visualization, we will virtualize and visualize everything. And last but not least, we're really at the moment into low code and no code. Why? And this is the next sheet I'll show you. This is our challenges at the moment. We have a few challenges within the company which are really predominant and which are actually in quite a few areas stopping us from progressing. The mental and the physical aspects of virtual and augmented reality. What's it doing with your head? What's it doing with your cognitive functions? It's uncomfortable. It's like wearing a big clog on your head the whole day. People can only wear it for an hour. You know, these are one of the things which are our barriers. We also have another barrier which we keep getting heard is it's product cannibalization. We are eating into our own product. I do not believe this. I can prove this is not true, but it's still a thing which is in the head of our people. We have an issue with usability. You know, onboarding somebody in virtual reality is not easy. It's time consuming. They have to learn the ropes, how the controllers work, and blah blah blah. It's really a challenge. We want to, especially with telepresence, we want that somebody has a red, a green, or a blue button on their headset, and they press the green button, they go to the green room, or they go to the blue room, or to the red room. We want to make it really easy. Hardware stability is also a big issue for us. Yeah. Oculus Quest 2s are okay, but it's still it's not solid enough for us. We don't want to. We tethered systems we don't like. And going back again to this, what I just said over the no code, low code, content creation. We cannot get enough devs. We have not enough people with Unity, C#, Python experience. We have to bring them from different countries now, or we have to get a lot of work. We have to put a lot of work out into Europe or wherever to get this done. It's really a really big issue. And content, if you look back to virtual travel again, it's going to be huge. So we need to get this under control, because this is a real big barrier for us. And security issues. As far as we know, at least, there are no standard standards, enterprise standards, which a company like the KLM, Air France KLM, needs to work safely in this environment. You know. Of course, you've got lots of security issues underneath, but there's no one company at the moment that's got an enterprise solution. You buy this headset and this works and it's safe. It doesn't exist, you know. At least we haven't found it yet, and we know there's lots of work going on about this, but it's not there yet. So it's really difficult for our company to take this on an enterprise way. And last but not least, I think probably our biggest challenge is what happens when they get over the wow factor, and when people start to realize, you know, first time you put it on, it's really cool. You can think about 10,000 things you want to do with it, but in the end, after a week or three, you know, it becomes normal. And what happens then? Where do we go then? What happens to everything which is going on? That's really a big challenge, you know. And this is in a nutshell, in the 10 minutes that I had, you know, if there are any questions, I will answer them. You can also question me offline, no problem. But these are the biggest barriers at the moment which we're facing regarding adoption within Air France KLM. We will overcome them, all of them, because, you know, most of these are engineering issues, you know, and the presentation before this one is also addressing a few of these issues, which I'm really glad to see. But it's a challenge at the moment, but it's going to happen. It's not if it's going to happen, it's a question of when it's going to ignite. So anyway, you know, in a nutshell, that's what I wanted to share with you. It's quick and dirty, but That's where what we're facing at the moment. Any questions?
Hi, yes, thank you, Mauricio. I'm very interested to hear how KLM is trying to innovate in different areas. So with regard to the use cases you have defined, which one are kind of the most important for KLM?
Use cases, we have in theory 3 use cases which are standing out at the moment. One is telepresence, virtual meetings. I think it's a very important one. The other one is XR maintenance within KLM. We have aircraft engineers who want to automate what they do using augmented reality, HoloLens, and Magic Leaps. And the last but not least, it's pure training. One of our biggest business cases is training of our pilot. We're trying to automate parts of the flight simulators. So these are expensive, and we can automate the ground procedures for our flight simulators in virtual reality. And we're doing this today, and it's really working. Does that answer your question?
Yeah, it's interesting. Communication coming from a company like Ericsson, which started by communication. It's interesting that you want to address the social VR part of telepresence. And so far, what are the level of quality that you are reaching with telepresence? Is about avatar, or is it really real representation of people who want to talk to each other, like a volumetric asset of the person?
Yeah. That's a good one. Of course, you guys are all technical, so you know that uncanny valley thing. That was a challenge, because we actually built our own system a few years ago within KLM for just to experiment, and we used the lifelike avatars. We literally, I was scanned. I was scanned, and a few other colleagues, and we noticed quite quickly this was not a success. So we went then towards using avatars. Which we still use today, and of course this helps enormously with the resolution as well, because we don't have the highest resolution. We're using Quest 2s and Valve indexes for virtual reality. We're starting to go now to HP, and we're using HoloLens and Magic Leap for augmented reality. But we prefer at the moment avatar-based telepresence, because it feels comfortable. Simple as that. And it works.
Thank you. So we have a question from Stefano Bonora. Are you using any technique to improve the comfort of the use of VR for long sessions? What's in the market we're using. We don't have anything special. What we do have in some of our lounges, we have they call it Sensix boxes. Where cold, warm, four-dimensional aspects are there. But it makes no difference. You can't get around the fact that these headsets are just not comfortable at the moment. They're just not comfortable. Even on a HoloLens, after a while, starts to hurt you. HoloLens 2, I'm talking about, starts to hurt your head. So we're noticing. We actually give the advice to our people who use these headsets. We say maximum 1 hour, and if you can keep it on your head for 1 hour, then you're really good. That's where we are at the moment. When we can't get further than an hour. Thank you. Any other question from the audience I would like to ask? We have a minute.
Yeah. What's the question?
No, I'm asking openly, but I see there is no more. Okay, well, I want to thank you. Yeah, it was very interesting to hear an industry trying to innovate with new technologies, which is always good to see, but it's also you bear the cost of being first, right? That's why we found very valuable to actually share that experience with us, because VRIF goals are to basically write guidelines with regards to the issues that you're actually facing.
Yeah.
And as along that come new technology, new immersive services, come new issues. Sometimes it's like a never-ending story, but we hope with the time it becomes better. And
what it is, we're dependent on you guys to make it better. Yeah, but we're users. We want to use the stuff. but you guys have to build the stuff that we can use, make it comfortable, make it okay, and then it's really going to ignite. If we don't do this quickly, we maybe might lose some momentum. That's my approach. Okay.
Great. Thank you, Jay.
Okay, and again, if anybody wants to contact me via LinkedIn, no problem. I can go into deeper details then, probably, if you have any questions. Okay.
Thank you. Yeah. So, want to thank to our speakers today. It was a very interesting discussion about presentation about volumetric and from research, trial, experimentation, standards, and real life experiences in the industry. I'm happy to see that things are going maybe a little bit slower than expected, maybe because of COVID. So just to remind you that everyone is welcome to join VRIF. Just have a look at the webpage. There's a lot of material that you can download without being a member. Just go to the webpage and you can see. And if you have any questions, please contact us. There are a lot of we have the contact details there. And for you to remind you that we will share these presentations in the webpage and also the recording. And by saying that, I want to thank all of you for participating, and see you next time when we have hopefully a physical workshop. Thank you very much. Have a good day.